So this is a typical example of unstructured programming, the kind of things that we did before this lesson. Now, having said these things, so this is in very brief, this is a structured design approach to RLL programming. Now, we must mention, since we are coming to the end of this programming part, we must mention that there are certain standards of programming languages which have come. For example, IEC 1131, IEC stands for the International Electrotechnical Commission, and the 1131 is a number. So, this is an international standard for PLC programming, and it classifies languages into two types. One are graphical languages, things like functional block diagrams or ladder diagrams. These are graphical languages. On the other hand, there may be several text based languages, for example, structured text or instruction list. These are some of the kinds of programming paradigms. I already told that although we are learning about the RLL, there are several other programming paradigms which are also supported by various manufacturers, and these are typical examples of them. So, for now we have understood that this state based design is very useful. So, therefore, to be able to capture this state transition logic, a separate language has been proposed, separate methods of programming, advanced programmings have been proposed, and we are going to take a brief look at that. So, some of the merits of this kind of advanced programming which takes this kind of abstract state transition logic, firstly because they have open standards, in the sense that anybody can write a program which can be used by somebody else. Then structuring of programs in terms of module helps in program development and program maintenance, very important. Program upgradation, you want to add a new functionality, you will find that it is very simple. Just change the state diagram and then find out that now in the new state diagram, if you have 3 extra states, simply you have to add those corresponding rungs. If you have some extra transitions, you have to add those rungs, and if you have to redirect some transitions to now new states, then you have to code that logic, that is that transition should now come in that state logic. So, you absolutely know that which are the places where you have to make change. These are the very standard benefits of structured programming. Then it is not necessary that all the times every rung has to be computed. In fact, only a few rungs are actually active and the other rungs are inactive. So, there is no point, you can save a lot of computational time by skipping those. So, this needs to be done, that will improve computational performance, and it supports concurrency. That is very important, that it supports concurrency, because it very often happens that there are many things, several things which will be taking place together, and which are best modeled as concurrent, and especially now that we have these so called multitasking operating systems or executives running on microprocessors. So, there is no reason why this cannot be done. I mean, we have the technology to enable it. So, therefore, we must use it. So therefore, we have a formalism which is standard and which are called sequential function charts. So, a sequential function chart is actually a graphical paradigm for describing modular concurrent control program structure. So, remember that it is basically used to describe structure and not the program itself. So, which part, so as if you have organized your program into a number of well written functions which are modularly arranged. So, you just using the sequential function chart, you are just describing that which of these functions will be executed when and under what condition. So, you have this remark which says that the SFC merely describes the structural organization of the program modules, while the actual program statements in the modules still have to be written, probably using existing PLC programming languages, something like either RLL or instruction list or whatever. So, let us quick look at the basic SFC constructs. They are basically state machine like constructs and contain some constructs which are which are simple programming constructs with which we are familiar. So, you have basically just like states and transitions, here you have steps and transitions. So, each step is actually a control program module which may be programmed in RLL or any other language. So, as I said, it is a function. Similarly, these steps can be of two types. Number one, initial step, I had marked the initial step, and the initial step execution can be of two types. One is when the first time you are executing after power on, and second is if a program reset, actually sequential function charts have some standard instructions which will reset, which are assumed to reset the program. So, after reset also you can execute a particular type of step called the initial step, typically used for initializing variables and states and intermediate variables. Otherwise, you have regular steps, which one of them are active at any time actually depends on the transition logic, as we have seen. So, when a step becomes inactive, its state is initialized, and only active steps are evaluated during the scan, that saves time. Now, we have transitions. So, in transition, each transition is also a control program module which evaluates based on available signals, operator inputs, etc., which transition conditions are getting enabled. So, once a transition variable evaluates to true, then the steps following it are activated, and we say steps because we, in this formalism, typically we have seen that one transition can go to only one step, provided you do not have concurrency, but since SFCs support concurrency, so it may happen that after one transition two concurrent threads of execution will start. So, that is why we have said steps following it are activated and those preceding it are deactivated. Only transitions following active states. So, again when you are in a state already which is active, only certain transitions can occur. So, therefore, only those transitions need to be evaluated. So, only those are evaluated. A transition can also be it can either be a program itself embodying very complicated logic, or it can be a simple variable like in our example, which is simple enough. So, for example, in this case it says that S1 is actually an initial step, and then if transition while S1 is active, T1 is active, and if the conditions for T1 are fulfilled, then it will come to S2. While at S2, if T2 will become also active, and if T2 occurs, then it will go to S3. So, you see that if you see the activations in scan 1, it may so happen that S1 and T1 are active, while in scan 2 it may happen that T1 has fired. Once T1 has fired, that is actually taken place because T1 is active. So, it has come to S2 and then T2 is active. So, if T2 is active, it is continuously evaluated. It may happen that in scan 3 T2 is evaluated to be false. So, these two continue to be active, while at scan 4 it may happen that T2 is now actually become true. So, therefore, S3 has become active, and then any transition outgoing from it will become active. So, this is in this way certain parts of the program at a time becomes active as the system moves through the sequential function chart. For example, there are you can describe several kinds of programming constructs. For example, this is an I am sorry. So, for example, this is a case where the system, if at S1 while the system is at S1, T1 and T2 are active. So, any one of them can become true, and if T1 is true, S2, the next active state will be S2. If T2 is true, the next active state will be S3. While it could conceivably also happen that T1 and T2 in a given scan, T1 and T2 both become active. So, in that case you have to resolve because both transitions cannot take place simultaneously. So, you have to say that, so there is a convention that the leftmost transition takes place. So, if T1 and T2 will both become active at the same time, true at the same time, then T1 is assumed to have taken place. So, that was a selective or alternative branch, that is the system can either flow through this branch or flow through this branch, but not both of them simultaneously. So, as I said that if S1 is active, T1 is true and then S2 becomes active. If T1 is false and T2 is true, then S3 becomes active, and then the moment S3 becomes active, S1 becomes inactive. Similarly, left to right priority, as I said, and only one branch can be active at a time. If S4 is active and T3 becomes true, S6 becomes active and S4 becomes inactive, same thing. Similarly, just like selective or alternative branches, you can also have simultaneous or parallel branches. So, this is a new construct which is not possible to be implemented in a normal state machine. So, this is the construct that helps concurrent control programs. The actual realization how you will run concurrent executions can be made using various operating system methodologies such as multitasking. So, here you have a parallel branch. So, when you see that at S1 if T1 occurs, then both these states become active together, and then at some point of time S4 becomes active, but T2 cannot take place unless this branch also comes to S5. So, only when S4 and S5 will become active, at that time T2 will become active and it will be evaluated. So, if it evaluates to true, then it will come to S6 and then S4 and S5 will become inactive. So, if that is the same thing is written here, if S1 is active and T1 becomes true, S2 and S3 become active and S1 becomes inactive. If S4 and S5 are active and T2 becomes true, then S6 becomes active and S4 and S5 inactive. Okay. Similarly, you can have among program control statements you can have jumps. So, for example, you have a jump where after S1, S2, after T3 it will go back to S1. Similarly, you can have a jump inside the loop. You can jumping here you can either come to S5 or you can come to S1. So, basically you can execute this kind of program control statements using SFCs. So, in jump cycle, jump occurs after transitions, and jump into or out of parallel sequence is illegal, because you cannot jump out of one sequence when you are in parallel. You must enter them together in any parallel sequence. While you are executing the sequence, you may be in different states at different arms, but you must enter them together and you must leave them together. Similarly, last you may have termination of a program. So, a step without a following transition. If you have a step out of which there is no transition, then it is a dead state, and once it is activated, it can only be deactivated by a special instruction called SFC reset. You can nest programming, you can nest a concurrent loop within a concurrent loop. So, here if T1 occurs, S2 and S3, then from S3 if T2 occurs, then simultaneously S2, S4 and S5 can become active, and if all of them are active, then T3 will take place and then S6. Similarly, you see here what is happening, this exactly the same thing is happening, that here you have a selective branch. So, you can have you can either go into S2 through T1 or go into S3 through T2. That is a selective branch. While you are in a selective branch, you can execute a parallel branch, and then if when S4 and S5 are both active, at that time if T2 evaluates to true, then you will come to a jump which will again take you to S1. So, such control flows you can specify. So, we have come to the end of the lesson. In this lesson, what have we learned? We have learned the broad steps in the sequence control design, and these are very important. That first of all identify the inputs and outputs, then very critically study the system behavior, look at the requirements for manual control, operator safety, faults, etc., and then try to formalize this description. So, first maybe write the operation in crisp steps in English, and then try to convert this description of steps into some sort of formalism, and we have in this lecture we have seen the formalism of sequential state machines which can be programmed using a sequential function chart. So, this modeling we have seen that how to model a particular application. We took a very simple industrial application like a stamping process and built its state machine, and then we have shown that how, given the state machine, how very mechanically you can arrive at a how you can actually structure your program and then write the transition logic and the state logic and the output logic, and we have seen that this is very much expected to lead to error free programs. And finally, we actually found a syntax, some language, graphical language, which can actually capture this flow of logic in terms of states and transitions. So, this program control or the program flow description strategy using sequential function charts we have seen. So, now before ending, I think it is nice to look at some problems. So, for your examples you can try to create let us look at exercise problem number 1. So, the problem number 1 says create an RLL program for traffic light control. So, what happens that the lights should have crosswalk buttons for both direction of traffic lights. Okay. A normal light sequence for both directions will be green. A normal light sequence for both directions will be green 16 seconds and yellow 4 seconds. If the crosswalk button has been pushed, then a walk light will be on for 10 seconds. If the crosswalk button has been pushed, then a walk light will be on for 10 seconds and the green light will be extended to 24 seconds, right. So, this is, see, this much of description is only given. Now, so what is the task? The first task would be to develop a state machine description and probably write it in terms of an SFC. And then while going to do this SFC, we will actually encounter several problems. For example, we may find that some things are not stated. For example, let us look at the SFC of this problem. So, we will, for the time being, we will skip problem number 2 or okay, let us look at problem number 2 next, and then we will go to the SFCs. So, the next problem says design a garage door controller using an SFC. So, the behavior of the garage door controller is like this. There is a single button in the garage and a single button remote control. When the button is pushed, the door will pushed once. When the button will be pushed once, then the door will move up or down. So, you push it once, it will move up or down. If the button is pushed once while moving, then the door will stop and a second push will start motion again in the opposite direction. So, you have a single button which you are going to push. So, you press it once, it might go up, press it again, it will stop, press it again, it will reverse. So, you have only one single button. So, you see that this is purely sequential behavior. So, unless you have a concept of state, you can never, you are actually pressing the same button, but sometimes it is stopping, sometimes it is moving up, sometimes it is moving down, and this kind of logic it is not possible to model using only input output. Then you have to bring in the concept of memory or state, as you might have noticed when you have designed digital logic circuits. So, you have sequential, whenever you have memory, you have sequential logic. So, let us look at then there are top bottom limit switches to stop the motion of the door. Obviously, you have pressed a button, it is going up, it has to stop somewhere. So, you have to have limit switches. there is a light beam across the bottom of the door. If the beam is cut while the door is closing, then the door will stop and reverse. So, if you have while the door is closing, suppose if you put something below it, then that is, you are trying to ensure that the door can actually close, because otherwise what will happen is that the door will get stuck. If you have kept anything there, suppose the back of your car is actually sticking out, then the door will go and hit your car. So, the door will close fully only if there is a light beam which is not interrupted, which means that there is clearance. Otherwise, if the light beam is interrupted at any time, immediately the door will stop and reverse. So, it will think that there is something, it cannot close it. There is a garage light that will be on for 5 minutes after the door opens or closes. So, so you have a garage light which can be open for 5 minutes after the door opens or closes. So, you have to use a timer here. So, any time you do an operation, the light is going to go on and stay 5 minutes. Okay. So, we have the two. Let us first look at the next one, which is simpler. So, here you have the garage door. So, let us see how they have modeled it. So, you have in this case, so if button is pressed, and so you have step 1 going to step 2 going to step 3. This is the closed door. So, if let us see, let us go back. So, there is a single button in the garage and a single button remote control. So, you can have either a button pressed in the garage, or you can have a button pressed in from the remote, right. So, there are two kinds of buttons. So, you have either a button pressed from the garage or from the remote, then it will go to step 3 and it will start closing the door. This is the output. On the other hand, if button has been, so if from there, if either a button has been pressed either from local or from remote, or if we press a button, what will happen? Then the door will stop. On the other hand, if the limit switch is made, what will happen? The door will stop. So, if either a button has been pressed or the bottom limit switch is reached, then immediately the door will stop. Or if the light beam is interrupted, then it will not only stop, it will actually reverse, right. So, immediately it is going to reverse. Here what happens is that if you have pressed a button and to stop it, then if you press it again, then it will go to reverse. So, this is a, you see, we have captured the behavior of the garage door in this form using SFC. So, you can do a similar thing also for the traffic light, that let that be an exercise. So, that brings us to the end of this lesson. Thank you very much, and see you again for the next lesson. Bye bye.